Hi, I'm Mark Kenny with Garage Gurus. In today's tech tip, I want to talk about validating VVT systems. We're working on a 2019 Chevy Equinox here, and there is nothing wrong with this vehicle. It's performing just fine. There's no codes, there's no issues or anything with it. So what I want to do is to show you techs out there a method that I use to kind of validate, does the VVT system have a problem, or is there an issue with change stretch? I get technicians asking me that question a lot. They say, hey Mark, how can you tell what the problem is? I've got this code for correlation between the cam and the crank, and how do I know what's causing it? So what we're going to do today is we're going to hook up our scope. I'll show you here in a minute all the different sensors we're connected to, and we're going to use our scan tool, and we're going to command the VVT system to change X amount of degrees. Today we're going to use 6 degrees. We don't have to move it very far to validate the system, but what we'll do is we'll actually take a scope capture before we move the phaser, and then we'll take one after we moved it 6 degrees, and we'll actually measure the degree of movement on our scope pattern to validate, did it actually do what we commanded it to do? Okay, so with all that being said, let's go ahead and get started. All right, we're over here at the vehicle now, and I want to take just a few minutes here to talk about our connections and where we made the connections, because that is a question I get from techs every now and again. They'll ask me a question and say, hey Mark, I really like those patterns that you have in that program, and I like what you're talking about, but how do I get that? Where'd you make those connections, and you know, kind of how did you set it up? So we're using a 4-channel Pico. I do get questions from techs also about scopes. Hey, I don't have a Pico, but I have, you know, an Altel, or I have a Handtech, or you know, whatever it might be. Could I still do the same test that you're doing? And the answer to that question is yes. You don't have to have a Pico to do what we're going to do today. That happens to be the scope of choice that we have here at the training center. And what I really like about it is it's PC based, so it works well with the computer there. It allows me to get good clean images and hook into our media when we're doing these kind of tech tips for you technicians out there. So we're using all 4 channels. And what I've done is I've actually connected, you know, different colored leads into different sensors so I can keep them all straight, which ones are which. So let me run through it real quick. The blue trace right here, channel A, is connected at the PCM for my crank sensor signal. You could go right to the crank sensor itself. You don't necessarily always have to go to the PCM. It's a little bit difficult on this one to get to the crank sensor. It's down underneath on the back side on this right side of the motor, and it's kind of in behind the manifold. Not super impossible to get to, but the PCM sits in this bracket right here. I've taken it out and kind of laid it over here to the side to make it a little easier. So obviously it was easier point to get to, so I picked that. My next lead, my channel B, is connected to the IC signal on coil number 1, and IC meaning ignition control. We're going to use that as a sync for our pattern, so we know where, you know, a number 1 is, so to speak. You know, this will make more sense in a minute. Our green channel, channel C, is connected to the exhaust cam sensor signal, and channel D is connected to the intake cam sensor signal. And by getting all these captures, what I'm going to be able to do is to show you the correlations between the number 1 firing event, the exhaust cam sensor, crankshaft sensor, and intake cam sensor. And by looking at those signals, we can actually create a pattern, so to speak. We're going to look at it and say, okay, we just need a reference point. We don't necessarily have to find where, you know, cylinder number 1 is on the cam signal for the intake or the exhaust. We're not really looking at that. We want to know if we move that phaser, does that cam signal actually change, and does it change the amount we tell it to change? So I just need a reference point. Now that could be the crank signal, it could be the IC signal. I could even compare between the 2 cam sensor signals. There's multiple ways of doing it. Today, what we're going to do is we're probably just going to look at the IC signal in relationship to the exhaust. I'm just going to do one of the VVT's phasers. And once you kind of see the process in action, you can do it on either one at that point. There's really nothing special I'm doing to the exhaust. We couldn't do the intake. So that's my hookup. What we're going to do next is we're going to get the vehicle started. We'll get the scope started, and then we'll actually jump in and do our tests. So what we're looking at right at the moment is the crank signal, and it's fairly clean, but there is a little bit of noise. So what I want to do is, let me go in here and let's turn on our filter, and let's filter this a little bit. It's not too bad right there. And then I'm going to change it to, we can leave it on a 10-volt scale, that's fine. I'm going to go ahead and turn on channel B, and since we know that's the IC signal, it's a 5-volt signal, let's just set it at 10, that way it doesn't overrange. And there again, I want to filter that one a little bit because we want some pretty clean lines for what we're trying to do as far as comparison. I don't want to filter it too much where I distort the signal. Okay. That doesn't look too bad. And let's go to channel C. We know those are 5 volts, so let's set those on 10 also. And do the same thing with my filtering there. Let's give it a little bit. Just want to clean up the edges so they're not kind of fuzzy, because like I said, we want to use them for comparison. You know, we're somewhat asking it to do some fairly precise measurements. So that looks pretty good. Filter it too much, it distorts the pattern. So I'm going to do the same with channel D, which we know is the intake cam sensor. So I've got that on. Let me move that one down here at the bottom a little bit. Oops, too far. Let's just put it right there. And let me filter that one just a little bit also, like we've done the others. Doesn't look too bad. So what I want to do now is I want to kind of arrange my screen a little bit. So let me move the crank up just a touch. And then we'll move our ignition signal up. And then I'm going to move the cam up just a little bit. Okay, now I'm going to need to change my time base because I'm a little too fast. I'm not getting the whole pattern in there. So let's change this to about 20 milliseconds of time, because I want to be able to see a whole 720 degrees of rotation, one complete cycle. And I think what we'll do is we'll set the trigger. Let's just set it auto for this second, and then I'm going to set it on B because I want to catch the IC signal. So let me set this over here, and then I'm just going to set it for a single shot. There we go. So we've got our capture here, and let's bring our markers in, and we're going to say that from this point right here to this point right here is 720 degrees of crankshaft rotation, which it is. That's one complete cycle. And you can see that this crank sensor is a typical GM. It's really got 60 teeth, but 2 of them are missing. So if you were to count these lines coming down from this point to this point, you would see there's 58 of them. And you know, I'm not going to count them. I'm just going to ask you to take my word for it, because there is. I did count them one time, and it is exactly 58, and that's kind of their reference point at this point. But between this ignition event for cylinder number 1 to this next event, that represents one complete cycle of the engine. We also can see that our exhaust cam, remember that's the one in green, lines up almost perfectly with the IC signal for number 1, as you see right here. So let me zoom in a little bit. Let's hit our zoom button, because this is our kind of where our reference is going to be. Okay. That's probably a little too much. Let's kind of manipulate this a little bit. And let's pull this down. And I think what we'll do is, let me minimize that. I might make this a little easier as if we switch these around. Let me bring this down right there. And let's move the exhaust up, kind of lay them on top of the crank pattern. Now there's a couple ways of doing this, because what we need is this picture right here. This is before we command it. And we know this signal here is going to move either in relationship to this IC signal or in relationship to the crank. And it's going to move in relationship to both. I shouldn't say either or, it will be both. So I could actually count, and let me get the pointer here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got 12 pulses, and then about halfway between them is where this signal comes back up on the exhaust sensor. And we know, well, you don't know, I do, but between these is, every one of these pulses is 6 degrees. What I'm going to do for today, instead of using the crank sensor, I'm actually going to use the IC signal. So we know this is my IC. It goes up, saturates the coil. This is my dwell time. And then it drops back to 0. Basically, it shuts off. That allows the induction to take place in the secondary windings and fire the spark plug. So all I need to know now is, let me bring these other cursors in, is how much difference is there between these two signals at the moment. So I get that right on there. Let's get this one right on there. And we've got roughly, if you look up here, about 1.3 degrees of difference. Now, one of the things that is a little bit of a variable for us, excuse me, is that ignition timing can change a little bit. When we run this test, they will kick up the idle, and it can change the timing a little. But we'll be able to validate fairly close, probably within a degree or two, did it really move where it needed to go? And to me, that's close enough. Usually on these vehicles, you're not going to have a problem until there's 6 or more degrees out before they actually start to code. So 1 or 2 degrees is well within our tolerance. So right now between the two, we've got, let's just say, 1.3 degrees. We can round that either up or down either way. So, all right, what I want to do now is I want to turn the scope on. Let me turn the zoom off, and let's make the scope live. And I'm going to go to the scan tool. So I've already set the scanner up. Didn't think I needed to go through that with you techs out there. It's pretty easy. This thing even auto IDs. So it's a 2019 Equinox, as you can see. Let me go back just one screen, actually a couple screens. You can see that I'm in this would be my opening screen, do my code scan, do all that. Go into my engine, go into functional tests, okay, because we've got our menus here. We're going to go to our functional test, and we got CMP actuator test. That's where I found this test that we're going to use. And we can test the solenoids, or we can test the actuators. Since we've already, we've basically decided we're going to do the actuators, so let's just pick this one right here. Now I can do exhaust or intake, and as I said before, because of the way the exhaust lines up there and everything, I thought, you know what, let's just use the exhaust position. So let me select that one. Needs to be in park. Yeah, we've done all that. And you might hear the engine pick up speed a little bit. When they run this test, they actually speed the idle up to about 1,000 RPMs. So right now I can actually put in how many degrees I want to move. So I'm just going to move it 2, 4, 6 degrees. Give it a second to kind of stabilize, and then I'm going to hit the capture button on my scope. Okay? And then I'm just going to back this off and exit out because it's going to time out. It only lets you run this test for so long. That's kind of the manufacturer's strategy. I think we can, if we look at the scope pattern, we can already see, if we're referencing the IC signal, turn off like we did, and the exhaust sensor signal. Remember how they were very close before? Now we can see the shift. We can actually see it shifted. So what I'm going to do is, let me get the zoom button, and let's just zoom in right here. It doesn't really matter too much which one we pick. And I'm going to kind of manipulate the zoom box just a little bit for us, because I don't need to see all that other stuff. Notice the shift that we have here. Okay, so let me minimize that. And what I'm going to have to do at this point is find my cursors. Set one here. Let's see. Oh, there's the other one. Let's bring this one over here. And I want to get it right on the edge. And we can see we're right around 8 milliseconds of time there. So we had 1.3 roughly before. We moved it roughly 6 degrees. It should have been about 7.3 to 7.5 in that range, and we're at 8.8. So we're about 1 degree different on our capture here from what the scanner actually commanded. And I would love to see it hit the number perfect. I'm kind of a perfectionist because of my machining background. But the reality is, if it's within 1 degree, that kind of does what I want it to do. That kind of validates the test for me. It did move. It did move roughly 6 degrees, maybe a degree more than I actually commanded. I can't say these tests are 100% accurate as far as, it's got to be this or else. I think we've kind of proven the point here that it does move. It does move very close to what we asked for. If we were to look at the variance, a lot of times when the phaser moves, it can be anywhere from 1/2 to 1.5 degrees anyway, and that's still acceptable for what we're trying to do. Remember, there's a lot of moving parts inside of there that, it's just gonna be what it is. So at this point, I've done my test. I mean, I could have, used this edge right here with my crank signal and done the same measurement there. Let's see what we kind of have for a number. We got 1, 2, let me get to the pointer here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 13. We were roughly in this area before. These are 6 degrees between them. You can see we've moved probably pretty close to 8 degrees that we were talking about right here. And there again, I see that movement. I'm within that 1 to 2 degree range of what I kind of see as a tolerance. And that tolerance is kind of a tolerance that I have kind of developed on my own from just looking at different signals. Remember, there's nothing wrong with this vehicle. This only got 23,000 miles on it. So one of the things I like about using these type of vehicles is, you've got good known patterns because the parts should not be worn. I mean, let's face it, within 20,000 miles, it should not have a whole lot of engine wear, engine problems, or phaser problems, or sensor problems, or anything like that. we should be able to use these as known good patterns. All right, obviously we got the vehicle shut off. We've got our captures. You can see I just kept it up here on the screen. And I think I did a pretty good job of illustrating how we can use some of those signals to validate movements. Definitely helps to, when you're doing these kind of demonstrations, to have a known good vehicle with no problems, especially one with low mileage like we're talking about here. It definitely makes it better. And having the ability to capture known good waveforms, this kind of information is worth its weight in gold to me. If I have to diagnose a vehicle and I'm looking at a signal I think is bad, it would be valuable to have a known good image that I can use. I'm Mark Kenny with Garage Gurus. For more helpful tech tips like this, check out our YouTube channel. And if you want information about Garage Gurus and training, go to garagegurus.tech.